All right, so now we move into chapter 3, and 3 is a long chapter. Let me see if I can scroll down. It goes all the way to 310. So there's a lot of material in chapter 3. And so it's all dealing with one-dimensional steady-state conduction. And we're going to first go back to the plane wall, just rectangular, one-dimensional heat transfer through a wall. And one of the concepts will come out with the thermal resistance. So some thermal resistance for heat transfer through a wall. And that thermal resistance is an L over Ka. Sometimes it's good just to memorize things. And so just L over Ka. And so what is my wall of thickness L? Thermal conductivity K. On this side, I have a given temperature, let's say T1. On this side, I have a temperature T2. So the driving temperature difference is T1. Assume that's greater than T2. Otherwise, just flip it around. But this is the, I'm just going to write it in the direction of heat flow from 1 to 2. T1 minus, let me do that, minus T2. And so what you say is the rate of heat transfer is equal to what drives the heat transfer divided by what resists the heat transfer, and that's our thermal resistance. We're not only going to do it for a slab, a plain wall, but we're going to go down and have for a cylinder and a sphere. Like put a layer of insulation on a cylinder, like a pipe, and from that inner to the outer layer of insulation, I didn't really draw that well, you can get an equation for that thermal resistance. And then you would have the same thing. You'd say, oh, the flow of heat is proportional to the temperature difference divided by the thermal resistance. All right. So somebody says, I'm going to solve the heat diffusion equation in rectangular, cylindrical, and spherical coordinates. It's going to be one-dimensional. Well, in the rectangular, it's going to be in terms of x, cylinder in terms of r, and sphere in terms of r. Those are our radial coordinates. That's our 1D direction. But I know you could have another direction like z or theta or phi, but no. Make life easy. Just r and r for cylindrical and spherical. It's steady state, no accumulation or depletion, and there's no heat generation, so Q dot's equal to 0. What is our general equation for all of these? Wouldn't it be something like K del squared T plus Q dot equal to rho C partial T with respect to time? So you just say, well, no heat generation, steady state. It's the one-dimensional Laplacian. That's what I need to solve. That's my governing differential equation. So for each of these systems, it boils down to, well, that K, you multiply both sides by 1 over K, and the K disappears. And so what you have is you have the second derivative of temperature with respect to x squared is equal to 0. That seems like a pretty simple differential equation. And for cylindrical, you have 1 over r, derivative with respect to r of r, derivative of t with respect to r, equal to 0. Not only like that k is sitting there multiplying, and we just multiply the whole thing by 1 over k. 0 times 1 over k is 0. So it's like it just disappears from this side. Same with r. 1 over r. You just multiply. Remember, I had this 1 over r. I multiply both sides by r. What's 0 times r? Still 0. So it goes away. This is our differential equation. And then in the spherical, you have 1 over r squared, derivative with respect to r squared, derivative t with respect to r, equal to 0. The same thing here. It's as if that goes away because you multiply both sides, and one side is 0. So you put the simplest boundary conditions here for a slab, going from x equal to 0 to x equal to L. And we're going to have t at 0 equal to t1, and t at L equal to t2, and t2 is less than t1. It's easiest to think about the flow going in that direction. And so those are my two boundary conditions. Likewise, for a cylinder, you'll have, this is R1. Think of T1 specified at R1. And likewise, come out to R2, and you specify T2 at R2. Two easy boundary conditions. Specified temperature, likewise the same for a spherical. I know it looks the same when I try and draw it, but at R1 we have T1, and at R2 we have T2. So I tried to draw out the whole equation and then say it's one-dimensional, no heat generation, steady state, very simple differential equation. The whole Laplacian, then the heat generation, etc. These terms all go, and that 1 over r even goes. Very simple differential equation, and likewise a very simple differential equation. Let's do it now for that plane wall. So as we set it up, it goes from x equal to 0 to x equal to L. We're interested in the flow Q, heat transfer from hot surface to cold surface. I know it's hard to sketch that cross-sectional area A, but that's what it is. Thermal conductivity K, and then thickness L, and specified temperature T1 and T2. So what is that temperature distribution? Second derivative equal to 0. What do I do to solve it with these boundary conditions? I separate and integrate. So separate, and you'll get dx is equal to a constant. Then separate and integrate again. You'll get t is equal to c1x plus c2. And apply the first boundary condition. You'll get that t1 is equal to c2 because x is 0 at t1. Let's put c1 times 0 plus c2. Fine. And then T2 is equal to C1L plus C2. So we have that C2 is equal to T1, and that C1 is equal to T2 minus T1 divided by L. So our solution for the temperature profile, T is equal to T2 minus T1 divided by L times X plus T1. Does that make sense? Let's check it out. How can you check this solution? Try it. Put in x equal to 0. What do you get for the solution? Back T1. Good, thumbs up. How about put in x equal to L? If you put in x equal to L, this is a bad looking x, isn't it? Let's try that x again. X. If the L's cancel, you're back with T2. Thumbs up. That's the analytic solution. Linear, straight line profile. It just would slope like this from T1 to T2. All right, so now that we have the temperature distribution, what is that rate of heat transfer through the wall? That's our Q. So Q is equal to minus K A dt dx. Do you like that equation? All right. What is dt dx? Yeah, it'll be T2 minus T1 divided by L. Isn't that dt dx? All right. So then we multiply by A. We have a minus K. And so at this point, we'll have Ka. We'll take that minus sign, put T1 because it's a greater temperature than T2. I think it's conceptually easy to put T1 hot. You don't have to. It'll turn it around and it'll flow be in the opposite direction. Then you'll have this. So this is our equation. Now, a little bit of name calling, and I'm going to explore this more on the next page, but you put Q is equal to what drives the flow divided by some resistance. And so this resistance is L over Ka. And that's a big deal. And once you get accustomed to thinking about thermal resistances and flows, that's the way we solve problems. It just makes it a lot easier, bookkeeping, and it's easy to think about it. So, how do they ever come up with this thermal resistance concept? Well, it's just like electrical resistance concept. So we go back to our simple 2 nodes, and then we have an electrical resistor in between. And then we have to remember somebody's law. The name of that person is OHM. Ohm's law, isn't it? Is it Ohm's law that we try to remember for how to characterize a resistor? So the resistor has resistance R measured in ohms. It has an EMF. I know this is always confusing to me when I took physics and introduced to electrical current and things like that. But electromotive force is probably easier to say, and it's measured in volts instead of saying my volts measured in volts. But that's the way I was taught, so it's a little confusing. But the EMF, what drives the flow, measured in volts, electromotive force. Okay, and then you can have it on this side. Let's put EMF1, or the electromotive force at 2, measured in volts. All right, so Ohm's law, how do you remember it? V is equal to IR, but is that just one V or a difference in volts across the resistor? It's a delta V, really. So it would be like V1 minus V2 to drive the flow through the resistor, right? Okay. Or, as I've written it, E1 minus E2, thinking of that measured in volts instead of V1 is 5V. That's always confusing to me, or I remember it to be confusing. The voltage at 1 is 5 volts. What? Anyway, okay. So this is equal to IR. Well, just write it like this. This is the flow of current is equal to what drives the flow, the difference in electromotive force, divided by the resistance. That's our electrical resistance. That's measured in ohms. So if I check my SI units, this is flow of current. Is that joule, or is that meter, or is that coulomb, or is that, what is it? Amps. Amp. And then our SI units for the delta E, volts. And then the SI units for the resistance, ohms. And that works. Remember that? So we have great confidence. We remember Ohm's law. And now we come over here and we have the same concept. We have a slab. We're going to talk about the temperature 1. We're going to talk about the temperature 2. Oh, by the way, the flow of the current is from the higher voltage to the lower voltage, the way we wrote it. But what happens if somehow in my circuit I thought E1 was greater than E2, but it's just the opposite? It'll be the negative flow, meaning it's in the opposite direction. All right. Same thing here with thermal resistance. And we just worked it out that we have the flow of heat equal to Ka over L times T1 minus T2, which is the delta T, what drives it. So we have that Q is equal to delta T divided by the resistance. And sometimes I put thermal resistance to distinguish it between electrical resistance. And that thermal resistance is L over Ka. All right. I think on the next slide I have a clicker question. Let me check and see if I do. No, I don't. Well, let me ask a clicker question. What would be the units of our thermal? Let's do this one. Is it watts? Is it watts per degree C? Is it degree C per watt? Or is it simply just degree C? What are my typical SI units for thermal resistance? We'll stop. Okay, let's just work it out. What are the SI units for the length? Meter. What are the SI units for thermal conductivity? Did I encourage you to just sometimes memorize something? You just memorize that, right? And so it's watts per meter degree C or watts per meter Kelvin, either one. because it's a temperature difference. And then the area is meters squared, so the meters go like that. And the correct answer is C. So you can do the same thing and get a thermal resistance for convection heat transfer. All right, so let's do it for convection. We have a solid surface with a solid surface temperature right here of Ts. And we have a convecting fluid that has a temperature T infinity and a convection coefficient H. For steady state, determine the rate of heat transfer from the wall to the fluid, assuming Ts is greater than T infinity. So you say, that's pretty easy. I wish all the questions in this class were that easy. HATS minus T infinity. Is that really our rate equation for the convection? There was somebody's name, I know it's not often used, but somebody's name. It's a law of cooling, and they say Newton. But Newton did so much that we just repeat his name every now and then, too much so. Some people just say it's a law of cooling, but other people will say it's Newton's law of cooling. Anyway, there it is. Now, you say, here's the pattern. Q is equal to delta T divided by thermal resistance. Can I identify a convective thermal resistance? What would it be? The convective thermal resistance would be 1 over HA. 1 over HA. Do you think the convective thermal resistance has the units degrees C per watt? You think that'll have the same units as the conductive thermal resistance, L over Ka? You have the same what is flowing. You have the same what is driving the flow. What's driving the flow is a temperature difference. What's flowing is a heat, is a rate of heat transfer in watts. Yeah, it's going to have the same, isn't it? Degrees C per watt. Okay, makes sense? Oh, there's my question. Well, I just answered it. Well, fine, let's press forward. Well, once you have the resistance concept, and often we have things that are in layers. So we'll have a wall, and maybe they attach some other material to it, or maybe another material. Think of material A, B, and C. And this whole surface over here is at temperature 1. Maybe this whole surface is at temperature 2. Or this whole surface is at temperature 3. This whole surface is at temperature 4. And they say, I want to know the flow through that slab. And if the area isn't changing, isn't this the same rate of heat transfer? The Q's would be the same. So maybe 50 watts of heat transfer through in a steady state. We're not doing transient. This is all steady state. It would be 50 watts through. So Q is consistent. Well, then you could just write and say, well, the difference, let's do this one, T1 minus T2 divided by L over Ka for slab A, or material A, or maybe I just put the resistance, thermal resistance for A, is equal to Q. And then I can say, well, Q is equal to T2 minus T3 divided by R of B, that resistance for slab B. And then the Q is equal to T3 minus T4 divided by R C. They could write it also as just Q is equal to T1 minus T4. What drives the whole flow through all of those three slabs? And here's the question. Let me ask this. This R right here, should that R be equal to either choice A or choice B? Is it equal to RA plus RB plus RC? Or is it 1 over RA plus 1 over RB plus 1 over RC, and all of that inverted? Do you understand the question? What is my equivalent resistance? All right, let me go ahead and stop. All right, so how would we do this? If I do this one, T1 plus, or let me do this one, T1 minus T2 plus T2 minus T3 plus T3 minus T4. What does that equal to? Is that equal to T1 minus T4? Yeah, isn't it? All right. Well, what is T1 minus T2? If I come to this equation, is that equal to RA times Q? Is T2 minus T3 using this equation, is that RB times Q? And is T3 minus T4 using this equation, is that RC times Q? Are these three Q's the same? Okay. Could I put this as RA plus RB plus RC all times Q? I know that I've got this equation. It's kind of like this, right? So could I then write Q is equal to T1 minus T4 divided by RA plus RB plus RC? So with that, which one is the right answer? A or B? A. Let's grade it. A. Okay, there's a little hint here. In all of these words up here, did anybody look at one of those words and say, aha, I remember something, and that helped guide me between the selection of A and B? Which word up there is it? Series. This is the solution for resistors in series. What is this, the solution for the resistors in parallel? And guess what we're going to do next? Parallel. Okay? When you're establishing a resistive network like this, find where you have temperature nodes. Didn't we talk about everywhere along this face is T1? And then put a node in corresponding to that temperature. Nodes in networks correspond to places where you can get a temperature, the temperature, like at a surface. And then you have over here, this is T2. Don't put nodes that represent fluxes. That's confused. Nodes represent temperatures, just like an electric resistive network. The nodes represented places where you had voltage measurements, EMFs, electromotive force measurements. What flowed between the nodes in your electric resistive network through resistors was the current. Here, nodes for a thermal network are representing the temperatures, and here I have 4 temperature nodes for this network. And then we had a resistor between. What flowed through the resistor? My rate of heat transfer. Just like my current, electrical current flows through electric resistors, rate of heat transfer Q flows through resistive resistors, thermally resistive resistors. All right. Just like that. And so I had 3 resistors in series. The sum of the resistors, each individual resistance gives me the equivalent resistance of the network. All right, let's go and do parallel. What would parallel look like? Well, let me do this. If I had a chunk and I had flow from this surface, which is all at temperature T1, to this surface, which everywhere is temperature T2. I could have it maybe go through material where this is all material A, and this is all material B, and then this is all material C. I'm trying not to change color too much to confuse you, but the flow could go from 1 to 2 only through A. Only has to pass through that A, which is in the upper part of the block, or only through B. which is kind of sandwiched in the middle part of that block, or only through C, which is in the bottom part of that block. This would be a concept of parallel thermal resistors. But do you see that each side of B and each side of C and each side of A, they all have T1 on one side, here I show it on the left, and T2 on the other side. So you would say, okay, here's my node T1, here's my node T2. I only have two nodes. I don't have 6 nodes or 8 nodes or whatever, just 2 nodes. And then I have the ability to go through material A, or the ability to flow through material B, or to go through C. And so I have that resistance A, resistance B, resistance C. And that equivalent resistance, if I said I want to make an equivalent, I can't spell, come on now, EQUI, equivalent system, I would just have one equivalent resistance. And that equivalent resistance, I think we already know, 1 over the sum of the reciprocals. So maybe I write it this way, like 1 over R sub A plus 1 over R sub B plus 1 over R sub C. Does that work? Sure, doesn't it? All right. Now, does this imply let me ask a question. True or false? Answer A or answer B? Is R sub A equal to R sub B equal to R sub C? Or R sub A not necessarily equal to R sub B, not necessarily equal to R sub C. They can all be different. Do they all have to be the same, or can they be different? Different. That's not true or false. It's just answer A or B. All right, looks like that wasn't too hard of a question. Everybody in? All right, let's go ahead and stop it. There's no restriction that they have to have the same resistance. So let me ask this. The flow of heat, let's say this is Q going through A, and Q going through B, and Q going through C. All right, we're talking heat transfer. What are the typical units for Qs, each one of those Qs? Watts. Watts. All right. Does Q sub A, must that equal to Q sub B? Must that equal to Q sub C? Or can they be different? Answer A or answer B? Same type of question. Do those Qs have to be the same? Answer A, yes they do. Or answer B, no, they can be different. They can all be. All right, so let me ask this question. I could let's say I make material A out of copper. Do you remember anything about the thermal conductivity of copper? Really high, really high. Let's say B is not only thin, but I'm making it out of wood. Wood, just pick some pine lumber. All right, so I'm making it out of pine wood, 2x4, or some material 2x6, whatever. It's thin and it's made out of wood. And the other is I'm making it out of glass, and it's intermediate thickness. True? In that case, do you think all the Qs are the same? Let me ask that same question again now. I make one out of copper, one thin layer of pine, one thicker layer of glass. Are all the Qs, the flow, the rate of heat transfer through the copper the same as through the pine, wood, through the glass? And we take a look at our results for this. So, which one do you think is going to be greater in this example where we put copper and wood and glass? The Q through the copper, the large slab of copper. It'll have a large flow of heat, maybe 100 watts, 1,000 watts, whatever it is. And the Q through the piece of wood will be low. So this proves to me that it's not only, it's sometimes the wording in the question that confuses people. See? I mean, I basically asked the same question, but a little different wording. And all of a sudden, our class, you move from sort of a C to an A+. How do you like that as a class? All right. Now, yes, sir.
Would the temperature on the other side be the same?
That's the challenge of having them in parallel.
Okay, that's what was confusing me because I thought since the temperatures would be the same on both sides.
Whenever you have a parallel, it's assumed that these have to be the same. Now you're saying, experimentally, how am I going to have to do that? Well, you're going to probably put a slab over here that's a really good conductor to help it stay the same. Or maybe you're going to flow fluid aggressively at that uniform temperature across that surface, aggressive flow of fluid to keep it the same. But yes, that's part of our assumption that those are the same. And if you were tripped up on that, yeah, I can see where that would lead you to try to make them different. All right. Well, you can, let me do this. Is the temperature difference across slab A the same as the temperature difference across slab B, the same as the temperature difference across slab C, or are they different? Clicker question, really fast. Answer A or answer B? All right, let me go ahead and stop it then. So actually I was forming that question when you asked me that question. And if you didn't notice, what question did I just answer? His question, which was the same as I was trying to pose. So, I don't know why two people. You're not one of the two, are you? Okay, thank you. I don't know why two people are playing with me. But you know what I can do now? I can go in and look at the attendees. I'm not going to do that in front of them and try to embarrass two people, but I don't know how to explain that better. I thought I did a good job of answering your question. Okay, if you come back here, you could play the same game. You can say, look, I could talk about the Q through A and the Q through B and the Q through C. Are they all the same or are they different? And I could talk about the temperature difference that drives the Q through A, and I can talk about the temperature difference that drives through B and the temperature difference that drives through C. And then I could talk about the resistance of A and the resistance of B and the resistance of C. And I can say either they have to be the same or no, they can be different, either one. See the same type of question? And you play that mind game, answer that question. For this, do the Q's have to be the same? Yes, they have to be the same. Do the temperature differences have to be the same? No. And do the resistances have to be the same? No. And then come back over here, the same thing. Let's talk about the Q's, the temperature differences, and the resistance. Do the Q's have to be the same? No. Do each of those materials, A, B, C, the different Q's. The temperature difference across? Yes. And the resistance, thermal resistance? No. Oh, see? Okay. Let's press forward. Well, sometimes you put a material slab and another material slab, and there's some resistance due to the contact between the material. That makes a lot of sense. I mean, if you ever did anything with electronics and played with computers, you want to put a heat sink on. Often they sell a little thermal paste to put on to help, but you don't want to put a thick thermal paste on, a very thin thermal paste on. Okay, well, what is this resistance? Well, let me do this. Let's sketch the temperature profile. Maybe I have the temperature in the y-axis, and this is a high temperature, and then it's going to be steady state conduction. It'll go like this, all the way to that side of material A, the right side of material B, which is on the left side of that interface. And then there'll be a significant temperature drop, I'm exaggerating it here, across that resistance, that contact surface because of some thermal resistance, and then maybe there'll be some other slope here. I don't try to draw these at the same slope because they could have temperature, they could have different thermal conductivities, and then they'd have different slopes. Sorry, let me try and draw it at a different slope. That one. I don't want them all to be at the same slope, okay? All right, so what's the constant, though, is the flow through the system. Q goes through slab A, through that surface contact, and then through slab B. And then they say, well, there's significant delta T in there. And so they're saying, you know, the delta T here has to drive the flow through that contact resistance. And so we have this model just like this. Now, if you want to do this, let's do this. Somebody says, I want to do Q, and I want to divide that equation by A. What does that Q in our book, what happens, what is that? What is our symbol for, it's our flux, that's our name, and our symbol is Q double prime, isn't it? Okay, so let's go over here. We're going to have this delta T. We're going to divide by A, and then we're going to have this R COND. All right, let me just help you a little bit here. What are the typical SI units of delta T? Degrees C, temperature change, Kelvin or C. What are the typical SI units for the heat flux? Watts per meter squared. All right. What are the typical SI units for area? Meter squared. What are the typical SI units for this R? Degrees C per watt. True? That's right. Now, somebody might say that I'm going to call this R conduction contact, maybe I put contact. Am I saying contact there? C-O-N-T. That's too many letters. Just put R-C. Okay, for contact. R contact. Times A. I'm going to call that R contact double prime. Do you see a kind of warping of syntax to do that? Because if I said, show me Q double prime, you'd say, well, that's Q divided by A. Somebody says, what's R double prime? Well, I'd take R and I'd divide by A. But not here. So always in engineering, you have to pay attention. There can be inconsistent uses of subscripts, superscripts, etc. You just have to really pay attention. This book has it right here. So they introduced this contact resistance, R double prime, subscript T, I like that, thermal for subscript T, comma, C, contact. That makes sense to me, the subscript. But what about that double prime? Well, this is the way they define it. We just worked through that, didn't we? And so the R double prime thermal contact in our textbook is really an area times thermal resistance, which has units of meters squared degrees C per watt, not degrees C per meter squared watt. Do you see a little challenge there? Yes, sir.
Do they have two materials in a problem? Do they specify what kind of resistance it is? Like, does it say it's thermal resistance, contact resistance?
Yeah, next slide. He's ahead of me, you're ahead of me. Okay. I prefer this notation, but it's not used in the book, which is a contact conductance with the symbol H. If somebody said, give me your best guess of the SI units for H, the letter H. It's like, well, the only other symbol I've seen heat transfer H is my convection coefficient. And my convection coefficient had watts per meter squared degree C. Yeah, and so basically, if you use contact conductance, which the book does not use, but many other books do use, I think it's a lot easier on the notation. So you'd say Q is equal to delta T divided by my H contact A, or I'm sorry, 1 over H contact A, or just put the H contact A delta T. But let's just say that we know that this is what's in our table and discussed in the book, and these are the units for it, and it's really the area times resistance, not resistance divided by area. Let's press forward. So this is a table straight out of our textbook. It has the thermal contact resistance for metallic interfaces under vacuum conditions. That's all in column A, vacuum interface. And then column B is aluminum interface with different interfacial materials. So let's get to B in a minute. Let's just do A. Okay. So if I have stainless steel and I have a contact pressure of 100 kilonewtons per meter squared, then the range for that thermal resistance contact, just like this, is 6 to 25, and then they have 10 to the 4, and there's your units. If I wanted it at this, maybe the lower value, and I said I have stainless steel at this pressure, what is R double prime TC? You have two choices. You would say it's either 6 times 10 to the 4 meter squared Kelvin per watt, or it's 6 times 10 to the minus 4 meter squared Kelvin per watt. Answer A or answer B? All right, let me go ahead and stop. Well, I thought I would have a cleaner distribution, but this shows me we're kind of all over the map. Did we not understand the question, or do we understand the question but not know how to answer it? What does this mean here? Often, I know it's not always, but often it means I took this value, I multiplied by 10 to the 4, and then I stuffed that into the table. So if you want the original value, you take the value out of the table, divide by this number 10 to the 4, which would be multiplying by 10 to the minus 4, and that's my value. So, all right. So now, this is also interesting. What is the difference between this column and this column? It's the pressure. It's that normal force per unit area pushing the two materials together. As I have a larger pressure, normal force pushing them together, does it help? What does it do? It reduces that contact resistance. Good, that makes sense. So a lot of times you clamp things together if you need it. Now this is all for a vacuum. And we just talked about, there's a lot of thermal paste to put in the interface. You keep it very thin, just enough to help a little bit. And so what is column B now? Well, they pick a particular surface roughness. They pick a particular aluminum material, 2 pieces of aluminum, with the particular roughness, because you can make it different roughness. And then, so with that pressure, with that roughness, with 2 pieces of aluminum, and what they do is they change the interfacial material. So, well, what is this? If I use, what is this fluid? Doesn't that give me a lower resistance? That's good. I'll have a smaller delta T. And then what about air? Well, air is a fluid. It's ubiquitous. There you go. So it gives me a higher value. So helium is a better conductor, so it drops than air. But both of these are gases. Hydrogen's a really good conductor, so it drops. That's all 3 gases. And then you have oil or glycerin. Okay. I know that sometimes I don't spend that much time on a table. I wanted to spend a little time on this table in case you have to solve a problem with it. So we want to fill in this blank of this statement that 10 to the 5th newtons per meter squared is either greater than, equal to, or less than 100 kilonewtons per meter squared. All right, everybody in? And I'll go back and I'll see, why did we ask that question? Well, back on this table right here, We have sometimes the data is given as, oh, this is 100 kilonewton per meter squared. True? But what about this interfacial pressure? Oh, no, that's given to be 10 to the 5 newtons per meter squared. And so you ask yourself, are these the same? Or which one's larger? Right? So the way you answer that question is you say, well, 10 to the 5, whatever, newtons per meter squared, is that equal to 10 to the 2 times 10 to the 3 newtons per meter squared? Is that true or false? True. Is that a kilo newton per meter squared times 10 to the 2? Is this 10 to the 3 a kilo? Yeah. And so the correct answer is, I'm going to ask that question one more time. All right, I'm serious about this. I want a few people to talk to me after class. I want those that selected A, I'm serious, I'm dead serious. Those that selected A and those that selected C, there's something wrong with your clicker. And I want to investigate it, okay?
Your thumb's too fat.
Well, your thumb's too fat or something. So we did improve, but there's 3 people I want to talk to, okay? All right, thank you very much. All right, let's press forward. Now, you can also have effective conductivity in the poorest material is where we need it. If you had a chunk of material like this, you'd say, well, where's my textbook? Where's my one value for this? Doesn't look like a solid block of copper or solid block. And so there's a lot of models, many, many models for effective conductivity, but some sort of effective conductivity based on porosity and how much of it is this and what volume fraction is this and how it's interconnected with the solid material. And I would just say, look it up. We don't have time to do effective conductivities in a wide spectrum of materials justice. But it's the reality of a lot of materials out there, and I don't want to bypass it, and then you say, well, I don't know anything about effective conductivities. Just know that I need to investigate it and be careful, okay, to get an accurate estimate of the thermal conductivity of the material. But you just get in one value for it, and then you treat it as a homogeneous material that's uniform. So now let's move to the cylindrical. So think about a pipe, and what is this on this pipe that wraps this pipe? Insulation. Insulation. What is the direction of heat transfer if the pipe is hot, containing hot fluid, compared to the colder outside air? Is the direction of heat transfer axially down the pipe or radially out? It's radial, it's not axial. So that's our one-dimensional direction. So we draw it like this. Maybe we have the center line, and then we have the radius going out, and maybe this is the inner radius of our insulation and the outer radius of our insulation. And maybe I try and draw the temperature profile and put T1 hot right there, and then T2 out there. Now, because the area is changing, it's not a straight line for that temperature profile. And because I have more area as I go further out, hard to see there, isn't it? Then I don't need it so steep as I did when it was less area. So there's a little belly to this curve. It's concave upward. Okay, so what we do is we say we have the mathematical tools to get the radial temperature distribution analytically. How do we do it? Well, give me a differential equation and 2 boundary conditions, and I can do it. And then once I have that temperature distribution as a function of R, could I calculate the rate of heat transfer through that layer? What law would I use? Fourier's law. True? And because the flow, at R1, that Q double prime is not the same as the flow Q double prime at R2. But if I multiply by the A1 and I multiply by the A2, then the Q is the same. The rate of heat transfer is the same as it goes through the system. Not the flux, but Q, the rate of heat transfer. So if I have 50 watts entering here, I have 50 watts leaving there. Okay? So that's the next step, is to calculate the rate of heat transfer. And then what you're going to find is that rate of heat transfer has a driving force to make it flow, T1 minus T2. That's the temperature difference. And then everything else in that equation, we're going to call resistance. It's 1 over R, right? So then we'll do some name calling and say, hey, I can get an R value for a layer, a cylindrical shell or a layer of insulation around a pipe. Okay? Now, that R will not be L over Ka. It'll be something else. It'll be with the natural logs. So let me do this in the interest of time. Jump over here. Here's the solution. Again, it's like mathematical weightlifting. You can do it. You just got to go in the gym and start lifting weights. So here's our differential equation, our two boundary conditions. What did we do in this step? Separate, then integrate. Get the constant of integration. Separate and integrate, get the second constant of integration. Then we have two boundary conditions. Unfortunately, you have two equations, two unknowns, and you may have to think about it a while to get the C1 and the C2 equations, and they have then the natural log of R1 over R2. And you'll probably have to remember that the natural log of R1 minus the natural log of R2, is that equal to the natural log of R1 divided by R2? How to combine them? Sure, yeah, we're going to use that trick or that mathematical relationship that we knew a long time ago. And so these constants, they're tricky, but then you get the analytic solution as a function of R. Here's R, and it goes between R1 and R2, and R1 and R2 are in the equation. And then you'd use this law. What is this one? Fourier's law. So I have to get the derivative of the analytic temperature. I multiply by, get this out of the way, multiply by the area, 2 pi RL, some cancel, and then I have a simple, and then I do a little name calling, and I call all of this 1 over R. And so there's my thermal resistance. Natural log of R2 over R1 divided by 2 pi KL. You can memorize that. It'll flow off your tongue pretty easy after a few times. L over Ka, and then here, natural log of outer resistance, the larger resistance, divided by the inner resistance, the small, not resistance, did I say resistance? The outer radius, R2, divided by the inner radius, R1. That's going to be a number greater than 1. If you remember, what is the natural log of 1 equal to? 0. What is the natural log of something like 0.7 equal to? A negative number. And so the natural log of something greater than 1 is a positive number. So this is all going to be positive. If you run your calculator and it comes out negative, you put in R1 over R2. Okay. And then you have 2 pi KL. 2 pi is easy. There's just constant K, thermal conductivity. L is how long of a section of the pipe I have. Not only can you do it for cylinders, like layer of insulation around a pipe, you can do it in a spherical. What's the roadmap to success? Get the temperature distribution, the radial temperature distribution. Then get that rate of heat transfer, Q. So get T as a function of R, then get Q through it, and then do some name calling. All right? So here is the solution. This is our thermal resistance in a spherical. 1 over R1 minus 1 over R2 divided by 4 pi K. And I know that there's a lot of work in this, but I'll show it to you, or it's shown here and covered in the textbook. Here's a summary. This is a very nice table. The bottom line, though, is that thermal resistance. If you have a plain wall, L over Ka. If you have a cylindrical wall or layer of pipe insulation, there you go. Or if you have a spherical shell, there. I know the Q's and all this are also there. But we started from our equation and then derived that. Okay. With that, I just want to say we're already through this part of Chapter 3. So please pay attention. Next time we'll move into energy generation, and Zach's going to start a quiz.